Section is going to be called the remainder theorem. It says to consider the polynomial function 3x squared plus 8x minus 4. They want us to divide the function by x minus 2, and they want us to compare it to what do we get if we were to plug x equals 2 into the equation. So we'll start by doing the division. For simplicity's sake, I'm just going to do long division as opposed to both. So we'll write x minus 2 equals, I'm going to divide that into 3x squared plus 8x and then minus 4. So x goes into 3x squared 3x times, so we distribute, get 3x squared minus 6x, close the parentheses, this goes away, and then we're going to get 14x. We bring down the minus 4, and so then once we do that, x goes into 14x 14 times. So we put a plus 14. We distribute, we get 14x, and then 14 times negative 2 is negative 28. And so then we subtract, these go away, and we get a 24. So that means my answer, right, is my quotient of 3x plus 14, and then we have a remainder of 24 over the divisor of x minus 2. So if we compare that to part B where it says find f of 2, and when it says find f of 2, what they mean is they are saying let x equal 2, right? And then it says find y. That's basically what that stands for. So we're going to take our function, which is f, and we're going to plug 2 into each of these places. So we're going to say 3 times 2 squared plus 8 times 2, and then minus 4. And then we'll just calculate that, right? To simplify it a little bit, this would be 3 times 4. This 8 times 2 is 16. We minus 4. This is a 12 plus a 16 minus a 4. We get 28 minus a 4, and we get 24. Right? The kind of the goal here is to see that there is a connection between these two numbers. Right? In one case we got a 24 in the remainder here, and here we have another 24 by plugging in 2. So then the other connection that they want us to see is the connection between here and here. Right, we had x minus 2 and we have 2. So the common bond between that, just to mention it, is x minus 2 is a factor. It's a factor, a potential factor of this. And so if we were to set it equal to 0, x minus 2 equals 0, we would get x equals 2. And so what are we testing? We are testing to see if we get a remainder of 0. Yes or no. It determines if something is truly a factor per se or not. In this case, we got a 24. So therefore, we did not get a remainder of 0. And so what the remainder theorem is basically proposing here is that if I took my proposed factor and solved it for 0, hence we got x equals 2, and I plug that into here, I have a shortcut way of finding if something is going to divide evenly into it or not, without having to do the long division or the reverse tabular division to find out if there is a remainder or not. And so this is generally what this section is going to allow us to practice. and C. So let's take a look at this one. It says divide G by x plus 1. So, okay, we can do that. So x plus 1, we're going to divide that into x to the third power minus 3x squared plus 6x, and then plus 8. So x goes into x to the cubed, x squared times. We distribute back to get x to the third plus x squared. We subtract. Negative 3 minus 1 is negative 4x squared. We bring down the plus 6x. X goes into here. Negative 4x times. So you get negative 4x squared minus 4x. And so these cancel. You get 10x. We bring down our plus 8. X goes into here 10 times. So you get 10x plus 10. We subtract, this goes away, and we get negative 2. So we find out by that word that there is a remainder. That remainder ends up being negative 2. So our answer is x squared minus 4x plus 10 minus 2 over x plus 1. But again, let's say I wanted to find out that x plus 1 is going to be a perfect divisor or not without having to do that work. Remember, if I took x plus 1, which is my proposed factor, I set it equal to 0, that means x would end up equaling negative 1. That's what we're testing right here. So I could plug this negative 1 into my function. So remember, we're saying let x equal negative 1. So we do negative 1 to the third power minus 3 times negative 1 squared plus 6 times negative 1 and then plus 8. So negative 1 to the third power is negative 1. Negative 1 squared is 1, and then 1 times negative 3 is negative 3. 6 times negative 1 is negative 6. And then we add 8, right? So this gives us negative 4 minus 6 plus 8. This part gives us negative 10 plus 8. And we get that same negative 2. So I was able to apply the remainder theorem by choosing a potential x value and plugging it in and seeing if it gave me a 0. In this case, it did not give me a 0. So then again, we would say that x plus 1 would not be a factor via the remainder theorem. All right, so number 3, same thing, right? 3 times is a charm, right? I always like to do it 3 times when possible. So we take our x minus 3. We're going to divide that into x to the third plus 0x squared plus 2x and then minus 3. X goes into x to the third power, x squared times. So this gives us x to the third minus 3x squared. This cancels out. We get a 4x squared, bring down the 2x. This gives me a plus 4x. So we get a 4x squared minus 12x. These go away. We get 14x, so 2 minus negative 12 is 14x. We get a minus 3. X goes into this 14 times. So we get 14x. Let's see, 14 times negative 3 is going to be negative 42. And let's see, I think we have a typo somewhere, just to see, because I feel funny about that. Because 2 minus negative 12. Okay, it's 14, yeah. All right, so let's just see. We subtract, this goes away, negative 3 minus a negative 42, and we're going to get 39. I don't know why. Oh, I see why. Let's go back. I had a copy error way back at the beginning. Right here. Want to make sure we get that right. 0 minus negative 3 is 3x squared, not 4x squared. We bring down our 2x. This becomes a 3x. So we get a 3x squared minus a 9x. This goes away. This will give us an 11x, which is what I thought I was going to get, minus a 3. So this gives us an 11. So we had 11x minus 33, and then we get 30. Right, same idea. Let x equal 3. So we have 3 to the third power plus 2 times 3, and then minus 3. So this gives us 27 plus 6 minus 3. And so then we end up with 33 minus 3. And we get that same 30. So then again, we were able to use that remainder theorem like we proposed in that idea. So number 4 says, find the value of k so that x plus 1 is a factor of p. So if you notice in the piece up here, consider the polynomial function, and we don't know what k is. But we want this to be guaranteed to be a factor. That means I have to take this, and I have to say x plus 1 equals 0. We find out that x is going to have to be negative 1. That's what we're going to plug in, so that y will equal 0, the function. So how do we manipulate that? Well, quite simply, we're going to let p of x be 0, and then we're going to plug everything else in. Negative 1 to the third power plus k times negative 1 squared minus 1, or you could say plus negative 1 if you want, and then plus 6. So essentially now, what we did, because we know we want this to be 0, that's the number we'll always look for if it's a factor or not. The only variable that's unsolved for is k. So this becomes negative 1. This is 1 squared, so this is 1, so plus k, minus 1, and then plus 6. So now you get 0 equals, let's see, negative 1 plus negative 1 plus 6. It's going to give us 4. So now we have 4 plus k. We're going to subtract 4 to the other side, and so k is going to equal negative 4. So that means for this to be a factor, I would need to have a negative 4 in this place. So that factor would be, this equation would be p of x equals x to the third minus 4x squared plus x plus 6. That means if I was to divide x plus 1 into it, it would guarantee to give me a remainder of 0, and hence be a factor in that design. So it says in part B, find the other two factors in that case. So now that we know and can guarantee that x plus 1 is a factor in that, we are going to divide and find out what the quotient is. So let's say this time let's do the reverse tabular. We haven't done that in a while. So we know we're going to need 2 rows, and then 3 minus 1 is 2. We add 1. We're going to need 3 columns. Okay, so we draw our box. We'll make a nicer box than that. We are going to put our 2 rows. Our 3 columns. Right, we'll slide this down just a little bit. And we're going to put our divisor, which we know is x plus 1. We're going to put our dividend around the side, which is x to the third minus 4x squared plus x plus 6. Now remember, in this perspective, we know that this is going to work and we're going to have a remainder of 0. So I can put an x to the third here. And so divide that, we get x squared. And just to go through the motions, right? This one divided, this would times this one is x squared. Just to put that in there. I need to think of something that I can do. And so this would be negative 5x squared. Because negative 5x squared plus 1x squared would be negative 4x squared. So this would give me negative 5x. So this one times this one is negative 5x. That'll make this one a positive 6x, because this one plus this one has to equal that one. And then we get plus 6, right? And I purposely avoided this one to show you that it works. 6 times 1 is, in fact, 6. So there would be no remainder in this case. So here's where we're at, right? We now know that x plus 1 is a factor. We knew that because we proved that up here. And now we know we have x squared minus 5x plus 6. So we can factor this one, x minus 2, x minus 3 would be our other 2 factors, right? So that would be the other 2 factors in this design. If we wanted to take it a step further just for fun, that means our zeros would be x equals negative 1, x equals 2, and x equals 3. That means if any of those into our original function, we would get a 0 for that. So let's say we consider the polynomial function this one. They want to know, is 1 a 0 for the polynomial? So algebraically, right, if we tested that algebraically, we would put, they want to know, is 1 a 0? That means the factor that we're considering is x minus 1. If we're asking is 1 is a 0. So we would just plug in, and we would say 1 to the 4th power plus 3 times 1 to the 3rd power minus 28 times 1 squared minus 36 times 1. We're going to add 144 to that problem. And so if we plug that in, that would be 1 plus 3 minus 28 minus 36 plus 144, and we end up getting 84. So the answer to this would be no. 1 is not a 0. So if we compare it to part B, if they give us x plus 3, that means x has to equal negative 3. So we want to know what happens if we plug negative 3 into each one. So that would be negative 3 to the 4th power plus 3 times negative 3 to the 3rd power minus 28 times negative 3 squared minus 36 times negative 3 plus 144, and then it turns out we will get 0. This is equal to 0. So the answer in part B is yes. Now it says the graph of P is shown to the right. What are the zeros? Meaning, where do they cross the x-axis? Well, we can see one of them here. That seems to be -6. We've got one right here. 1, 2, 3. It's -3. We've got one right here. That's a 2. And you got one right here, which is a 4. So we'll write and 4. So they say write an equation in factored form, right? In factored form, right in the factor. So if these are my zeros, I can rewrite this as factors. So I could say P of x, because they said the equation of P. So we say P of x. We're going to change this 0 to a factor by writing x plus 6. We're going to change this -3 to a factor by saying x plus 3. We'll change this 2 to a factor by saying x minus 2. And we'll change this 4 to a factor by saying x minus 4. This would be the equation written in factored form. We don't need to multiply these together because they didn't ask us to write it in standard form. They just said factored form. Okay, final exercise. It says consider the graph of a 5-degree polynomial shown to the right with the x-intercepts of -4, which is here, -2, which is here, 1, which is here, 3, which is here, and 5, which is here. Notice the degree matches the number of zeros that we see in the graph. They say write a formula for a possible polynomial function that the graph represents using c as the constant factor. So the way this would look is we would write P of x equals, we don't know what the constant factor is in front, and so it would say x plus 4, x plus 2, x minus 1, x minus 3, and x minus 5. So this would be our function. Now let's say in part B, suppose the y-intercept is -4. That means if we have a y-intercept of -4, that means it's crossing approximately here, which means we have -4 or 0, -4. 0, comma, -4. Then wants to find the value of c such that the graph has that y-intercept. So we can do that. So since this is y, we say -4 is equal to c times 0 plus 4, 0 plus 2, 0 minus 1, 0 minus 3, and 0 minus 5. So that means this is c times 4 times 2 times -1 times -3 times -5. And that's going to equal -4. So we multiply all that together. 4 times 2 times -1 times -3 times -5. And we're going to get -4 equals a -120c. So that means we divide -120 to the other side. So I'll just write this over here where we have room. That means c is going to equal -4 over -120, which ends up being 1 over 30. So that would be the value of c. Okay, that's all there is in this lesson. Remember we talked about the remainder theorem. That's where we could take a potential factor, set it equal to 0, find out what that potential 0 is going to be, and plug it directly into the equation and see if y equals 0. If it does, it tells us it's a factor without having to do spending our time doing long division or reverse tabular to find out. And then we looked at zeros on the graph, and we wrote some functions in factored form. So that is all for lesson 19.